Organic chemistry is the domain of physical sciences associated with the structure of carbon-containing molecules and their reactions. At the beginning of the field in the 19th century, organic chemistry was distinguished from other disciplines not based on the chemistry of carbon, but rather on the study of matter derived from living systems. Ultimately, it became clear that the chemistry of life is a subset of the chemistry of carbon. In this lecture series, we are discussing how to alter the chemical composition of the cell using genetic engineering. Thus, you need to understand some basic concepts of organic chemistry, so let's recap the critical points. When you examine a petri dish, you are looking at clumps of around 1,000,000 bacteria. When we zoom in here, you can almost make out one of these bacteria from the colony. If we look closer with an electron microscope, we can see the individual bacteriums more clearly. If we zoom in further, we get to a size scale that is no longer visible by traditional microscopy, but artists can illustrate what goes on inside the cell. We see individual proteins, the membrane, and a flagella. If we zoom in yet further, we get to the atomic level in which molecules like protein, DNAs, and metabolites all have very specific configurations of covalently and non-covalently associated atoms. The world is made of tiny balls, called atoms, and other fundamental particles like electrons and photons. It is not continuous. From physics, we know that atoms are themselves made of yet smaller balls, and in nuclear reactions, atoms can be split or joined and thereby change identity. However, at the energy levels that exist in the biological world, nuclear reactions do not occur, so you don't need to worry about anything smaller than atoms. Atoms interact with each other in stable configurations on two different energy scales. The stronger interactions, called covalent interactions, have bond energies on the scale of 300 kilojoules per mole. The other type, non-covalent bonds, are much less stable with energies on the scale of 20 kilojoules per mole. In the context of the dynamic water-rich environment of the cell, the energy difference between covalent and non-covalent bonds is even more pronounced. Since we are dealing with many punctate atoms and the pairwise edges that connect them, we can describe the cell as a big network of atoms and bonds. We can also describe aggregates of atoms within that network and describe the structure of these connected subgraphs. When we speak of the graph that results from covalent bonds between atoms, we call that a molecule. When we speak of the graph resulting from non-covalent interactions between molecules, we call that a complex. The remainder of what is happening in the cell is defined by the Schrödinger equation. This equation from quantum mechanics describes the energies and waveforms of the electrons surrounding the atoms. It describes the various states that the electrons will exist in. Chemical reactions involve changes to these electronic states and transitions of electrons between these states. The problem with Schrödinger is it turns out to be really difficult to solve. It can only be solved exactly for trivial systems like a hydrogen atom. It can be solved numerically, but it's computationally intensive. Physical organic chemists will often use such calculations to help them understand observed reactions that defy simpler explanations. However, simpler chemical theories such as VSEPR can explain the great majority of the chemical reactions that happen in biological systems, so we will focus on this theory. The VSEPR theory is the one that deals with hybridization on an atom. It is the theory whose consequences are physically encoded in the components of a chemical modeling kit. To make a stable molecule, minimally all the holes in the atom pieces need a bond placed in them. Every end of the bond piece needs to be attached to another atom piece. The simplest rule implied by these kits, that carbon likes 4 bonds, oxygen likes 2, nitrogen likes 3, and hydrogen likes 1, are almost always true in the chemical reactions observed for biological systems. Additionally, this view of chemistry implies the existence of 2 types of bonds, sigma bonds and pi bonds. These bond patterns can be understood as pairings of orbitals between the atoms. When a carbon, oxygen, or nitrogen atom exists in the sp2 hybridization state, it can use some of its available electrons to make double bonds. When something happens in a biological system, it is ultimately being implemented as many chemical reactions. That is most obvious during the biosynthesis of chemicals, but it is also true when you say, bend your arm. You are breaking oxygen phosphate bonds in many ATP molecules and modifying the structural state of proteins within your muscle cells. So we need to understand what chemical reactions can occur. Chemical reactions define a change in the structure of participating molecules. There is a state to the atoms involved before the reaction, and there is a state when it is complete. The difference in energy between these two states is called the Gibbs free energy, and when it is negative, the reaction occurs spontaneously. During a chemical reaction, neither atoms nor electrons can be created or destroyed. They are simply being rearranged. So the total count of atoms or electrons is conserved across the two sides of the equation. What happens under the arrow of the chemical reaction is not arbitrary. There are precise geometric events occurring on these molecules. The atoms don't just fall apart and rearrange, they must react through a constrained set of mechanisms such as nucleophilic substitution or elimination. In organic chemistry, the number of mechanisms available is fairly rich, primarily because transition metal complexes, these are things made with carbons bonded to atoms like palladium, they do fancier things. However, these molecules aren't stable in water, so there are very few mechanisms available in biological systems. Most biological reactions fall under the categories of nucleophilic substitution, elimination reactions, or addition reactions. Reaction mechanisms can be represented visually using arrow pushing. The link here describes how it is done in more detail. Bond-breaking arrows originate on a bond and point to the atom that will receive a pair of electrons. Bond-making arrows initiate on a lone pair of electrons on an atom and point to the atom they will become bonded to. Biochemists often use arrows in ways that don't actually mean arrow pushing. For example, here the scientist is showing the movement of a proton from an acid to a base molecule. To draw this more accurately, the electrons on the base should be attacking the proton, and then the bond between the H and O should be broken with the electrons returning to the oxygen. In the product conjugate base, the electrons are not distributed across the entire hydroxide molecule as implied. They are localized to the oxygen atom. So the point here is to be a little careful in reading the diagrams and figures. Sometimes people use the notations of organic chemistry loosely.